So hi all, good morning and good afternoon and good any time, like wherever you are. My name is Tejendra Veer Singh. I'm Chief Computational Scientist at UCLA Office of Advanced Research Computing. So I welcome you to today's event organized by Early Career Researchers. Please be aware that we are recording the session. Today's session is by Dr. Bryor Snefjella. He's presenting his work, creating a comprehensive lexical resource for English using Bayesian, deep learning, and missing data methodology. He's an IDRI scholar and a postdoctoral researcher in the psychology department, Blanc Lang Lab. He is mentored by Professor Idan Blanc, Keith Holyoke, and Hong Jing Lu. Before coming to UCLA, Bryor received a PhD in cognitive science of language from McMaster University in Canada. His research on language use patterns in social media has received international media attention. So it's a really interesting topic. Hope you will all enjoy and learn something new. And just before I give the stage to Bryor, I want to mention that please mute yourself if you're not talking. And if you have any feedback, comments, or questions, use the chat box. We will take those after the presentation, or depending on Bryor, he might take those in between. So thank you again, and over to Bryor.
Hi, everybody. Thank you for coming. So what I'm going to talk to you about today is, because this is for a general audience, a brief review of the cognitive science of words. I'm going to talk about how much data we have on English words and why I think missing data methodology is the sort of secret sauce of how to actually create usable computationally extrapolated linguistic resources. And I'm going to talk about how natural language processing automates the measurement of meaning, and the Bayesian deep neural network that's at the center of making this resource. And I'll present just a couple of little showcases of the data. So first, just briefly, to talk about how we study words. When you think of, a big store of meaning, you probably think of something like a dictionary, this static, unchanging list of words in a book. But cognitive science thinks of the lexicon, the mental lexicon, or store of knowledge about words, usually in a much more interactive way. There are different models, but they all kind of share this similar idea of an interaction between semantics, meaning, phonology, how words sound, and if the language has a writing system, orthography, and as well as the context in which words are used. Different models imagine that the representations of semantics, orthography, and phonology have different form, or that they interact in different ways. But this is really what we imagine: this dynamical interaction between these components. So the kind of questions people ask are, let's say what the structure of the semantic network is. There's many kind of different notions of different kinds of semantic networks that could store meaning, a hierarchical organized set of features, or a densely connected network, or, a network where there are these important nodes, for example. As well, there's a big question is the sort of division of mental labor and the relationship between the mental lexicon and other cognitive systems in the brain. Is there, for example, a meaningful distinction between linguistic meaning and a concept, or are those synonymous? We study these kind of questions in a variety of ways. For example, neuroimaging. So you can, for example, if you put electrodes on somebody's scalp and amplify the electricity present on the scalp, you can find that you get little spikes of electrical activity when people are exposed to pleasant and unpleasant words, in the same way as when you show people, in a similar form to when you show people, say, unpleasant or pleasant pictures. So your brain acts, when I show you the word knife, the same, almost, in a similar but blunted way as if I were to like brandish a knife in your face or show you a picture of a knife. As well, we use lots of behavioral measurements. So this is an example of one kind, called eye tracking, where you have a specialized camera that records the position on a screen that people are looking as they read text. And what you get out of that is, for example, these are two sets of eye movements from two people. The size of the dots indicates how long they fixated on that word, and the lines are the jumps between fixations. So you can use this kind of behavioral data as an index of the difficulty of processing different words. And there are kind of many, many, many different behavioral tasks that are used. As well, there are traditional sort of survey methods. So there's this famous work on what's called a semantic differential by Osgood, a famous book called The Measurement of Meaning, where the idea is you take a word, like say in this case it's energy, and then you create a bunch of scales, and you get people to rate the word along all these scales. And this has inspired sort of decades and decades of different constructions of different kind of surveys, all designed to capture sort of important components of meaning. So one that's studied quite a lot is called concreteness, which is whether a word refers to something that's sort of accessible to the senses or not. So these are sort of a little sample of very concrete words from one data set and very non-concrete abstract words from a different data set. And there's this famous thing called the concreteness effect, which is that concrete words are easier to memorize, learn, and recognize than abstract words. As well, a really common method that's become really big with the invention of the internet is that we have, as linguists and cognitive scientists interested in language, we have our telescope for the first time, in effect, and that is the internet, and particularly social media and the billions of words of language use that are recorded now on social media. So we have the ability to extract information on how often words are used, the consistency of word use across contexts, and how often words share contexts. Those are respectively called frequency, dispersion, and collocation. And this is very rich data for effectively modeling the linguistic environment in which speakers inhabit. So to summarize, we're interested in three main kinds of data when we're studying the cognitive science of words. They're brain behavioral responses during word processing tasks, annotations of words for semantic or other features, measures of frequency, dispersion, and collocation from corpora. And we want to use all these kind of data to understand how words are represented, processed, and used. That's the kind of what's at stake in terms of the science. So now you could ask, okay, so how much data do we actually have on English, which of course, being a lingua franca and this very dominant language is really the most studied. The answer is actually surprisingly little. So I'm going to show you now data from something like 450 open source data sets, each containing some kind of measurement of some interesting quantitative facts about a word. Note here that the y-axis is logarithmic. And what this plot is going to show you is how many words are in each of those data sets. And I will say here, this line is the size of an average English speaker's lexicon, how many words an average English speaker knows. So here's the data we have. So we have a handful of measurements. These are frequency and dispersion measurements from corpora, where we have, tons of data, lots of things we wouldn't even call words, like periods and emojis. But then very quickly, you start running into cases where we have like a third of the amount of data that an average English speaker knows. And then actually the majority of open source data on English words is just missing. There's this really long tail, right? It's like a logarithmic decrease, because this is log scaled and it looks roughly linear in the amount of data we have. So effectively, most data sets are really tiny. And what tends to be hidden out in this long tail of tiny data sets is, I think, the really interesting stuff, which is lots of stuff about semantics, word meaning. So what I try to do is turn the data we have into this comprehensive, complete data on English words. So the question you might ask is, why is this hard? Why can't we measure everything? And the answer is cost. So if you pay, this is just for the survey data about semantics. So if you pay a person online a cent for a judgment about a word, and there are 40,000 words, you need 30 of those judgments to get a stable mean. There's something like 100 of these scales in the literature. We would like to have this for 10 languages. There are 3 different ways, 3 different measurement formats in the literature for these kind of data. There are 5 ways people vary very conservatively that are interesting. And let's say, okay, we don't need the full lexicon, we need only 5% of it. You still wind up with a cost of $9 million. So really getting comprehensive data on the scale of an entire language gets very expensive very fast. And the question you might ask then is, do we really need all the data? And I think the answer is actually yes, for a couple of reasons. One has to do with the distribution of how often people use different words. It's this famous thing called Zipf's law, where, and again, this is log scaled. There's sort of a small number of words people use a ton, like the and it and. But then there's this really long, huge tail in this distribution of exceptionally rare events. These are, specialized words from different jargons, new words. I think if you're a linguist, the interesting stuff. And we tend to have way less data on these rare events, but these rare events can make up something like 30 to 50% of the total probability mass of the word frequency distribution. So there's a huge number of rare events that we just miss, is my argument. And that's what we want to actually capture with a comprehensive resource, the full picture of the lexicon. So that's how much data we have on English words, right? We have quite a bit, but actually still we're missing most. So why then do I think missing data methodology is kind of the key to getting kind of all that data without needing to just measure it all? So missing data methodology, very briefly, deals with estimation under these conditions. So theta is some parameter we want to estimate. X is a matrix of complete data, and X observed and X missing are the same data matrix, but some observations are only partially observed and some are complete. Then missing data methodology wants to do statistical estimation such that we converge to the same theta, regardless of if the data is complete or missing, right? This is sort of a mathy statement that the scientific conclusions we make should not be influenced at all by the presence or absence of missing data. We can't expect to estimate theta as efficiently when data is missing, but we still want to get to the same theta in the end. So we can ask is, does the status quo for how people in this field deal with missing lexical data satisfy this property? Does it give us this kind of estimator? And I think the answer is almost certainly no. Because the default approach that we tend to do, and I myself, I'm pointing my finger at myself here, I've done this in papers, is a thing called complete case analysis, which is where any row of your data matrix that has one, even if it's 99% observed and there's one little missing data point, you just discard it, don't analyze it. Only analyze the data that's complete. But this only yields a consistent estimator if the observed and missing portions of your data are drawn from the same population. This is known as the missing completely at random MCAR assumption. So I think this assumption is almost certainly false. What that means is that we should really expect substantial biases in the existing literature on words as a result. We're effectively under constant sampling biases. And I can show you this, I think you don't even need data to really see this. You can read papers and see that people select words non-randomly, but you can look at it as well. So what you're looking at here is the y-axis is across all of those 400 plus open source data sets for a given word, what proportion of its vector of data is complete or observed. And the x-axis here is a measure called word prevalence, which is the z-scored proportion of people who say they know the word by mass scale vocabulary testing online. So 0 here means 50% of people know the word. And so what you see is that if a word is known by less than 50% of English speakers, it has almost completely missing data. And even when you get up to the words that everybody knows, it's pretty common for something like 80% of that word's vector of data to be missing. So this is not good, right? This is systematic missingness. We're missing those rare words. This is the same thing, but now with word frequency as measured in a corpus, where, again, those words in the tail of that distribution are almost completely missing their data. And we even wind up missing as well a lot of semantic data for the frequent words, because people never ask, like, how concrete is the word the, which makes sense, except if your goal is to correct for missing data, that's actually useful information that the should have a 0. We'd like to know that. Even more problematically, you can also predict how missing the data is from the dependent variables that we consistently analyze in this field. In this case, this is the response time from a behavioral study, a huge behavioral study. And so what it shows is that, again, words with long RTs, the words that are difficult to process, tend to have much less complete vectors of data. And missingness conditional on the dependent variable you analyze is just a recipe for all the coefficients in your model changing. Again, substantial bias. So the better assumption to make, I think the field needs to make, rather than MCAR, is called the MAR assumption, missing at random. It's kind of an annoying name. It's a misnomer. It's different from missing completely at random because it says, if we condition a model on our observed data, then, and to predict the missing data, then the probability of something being missing reduces to 0. So in other words, the observed data we have is sufficient for accounting for the missingness. You can't prove that this assumption is true from data, but it's, I think, the default assumption that most missing data methodologists make, and I think it's the one we should make. And this is, again, why we need to actually fill in all those missing data points to correct for those sampling biases. So what then this thing, the English Lexicon Imputation project that I've created is it's an imputation model that uses the sum total of this observed English data on words to fill in missing information on English words. And so it asks this question: what if more than 60 studies of English words, again, containing something like 450 measurements, had used every word in English as their stimuli? And it makes these unique design choices inspired by the literature on multiple imputation to try to satisfy get this estimator that we want. So we converge to the same scientific conclusions as we would get if we could actually go out and just measure empirically all of this stuff. So that's why I think missing data methodology is the secret sauce. It gets us to what we actually want, which is the same scientific conclusions as if we empirically measured everything, hopefully, if we do everything right. Okay, another component of this has to do with natural language processing, NLP, and how it handles this challenge of measuring meaning at mass scale. And it does it a different way than most cognitive scientists. It does this with a thing called distributional semantics, which is, yeah, I'm sorry, this is the question I'll answer here, how we do this. So what is distributional semantics? Well, if you look within a corpus of natural language at co-occurrences between words, you notice systematic relationships. So I'm not doing words here, but emojis, just so it's visual for the sake of the presentation, but the same principles apply to words. So you notice here that, for example, the different hand emojis, because they share a kind of meaning relationship, often co-occur together. Same thing with two emojis about being sad, these other emojis about negative emotions. So even not having any information on the meaning of a symbol, co-occurrence between symbols can tell you that they have some kind of related meaning. The distributional semantics tries to extract latent factors that explain co-occurrences between words in databases of billions of words of text. What you get out of that is what's a semantic space. And again, I'm showing you this with emojis, but it applies to words too, where the position of each emoji in this semantic space is determined by its distributed pattern of co-occurrences incorporated with other emojis. So all these flag emojis are effectively, they co-occur with a similar pattern of emojis. Likewise, the face emojis are in one cluster here. This is a simplified depiction in a two-dimensional space. When you do distributional semantics in practice, you're often dealing with a very high dimensional space, often 300 dimensions. But the same principles apply, that the similarity in meaning can be captured by a distance in the space derived from shared co-occurrences between symbols. And this is again an example that does use words, where again each cell in this matrix is going to represent co-occurrences between the words. And there's been some clustering done on those co-occurrences, and you can see that the words with kind of related meanings get clustered together. So this is how you automate the measurement of words and their features, including their meanings. But there's a big limitation here, which is that these things called distributional semantic models yield features that are just hostile to human interpretation. And they're entirely data-driven. They know nothing about, theories of word meaning from cognitive science. And so here's, what the data looks like. Again, it's kind of like, the word data I showed, where there's just these arbitrary dimensions, and like you can't look at these numbers and like see anything and drive anything. So here's, for example, the top and bottom words of one of the dimensions in this space, right? And I can't see anything systematic about why these words would be at the pole of one dimension and the bottom pole of another. It's just, you can't interpret it. But there's tons of rich information about word meaning in there, which is why these are ubiquitously used in natural language processing as representations for words. So what you're looking at here is just the word dog, and it's the correlation across these dimensions. So the correlation between, this 300-dimensional vector for two of these, for the words, in this case, dog, and a bunch of words, and you can see that you get this beautiful, collection of words that are synonyms or semantically related to dog. So there's rich information about word meaning in there. It's just you can't find it in the features if you're just a mere mortal. So what a lot of NLPers and computational linguists and even cognitive scientists have thought is that you can sort of merge together the kind of traditional survey methods and this distributional semantic method into sort of Frankenstein's statistical monster. Which is why I'm doing this joke here about the pigeon rat from The Simpsons. What you do is you train one of these DSMs on corpus data, and then you develop a model that predicts for each of your jth, lexical feature with missing data, some model that predicts that feature from the features of the distributional semantic model. And the reason I do this superscript J in each case is that the way this is almost always done in NLP is that every feature gets its own independent model. And F in this case is just some kind of supervised machine learning, random forest, linear regression, whatever. What you do then is that each missing cell in your data, if you're an NLPer, is you impute it once deterministically with the conditional mean of your model trained on the DSM features. And this is where I think things are really problematic, and you need the missing data methodology to guide you, because this imputation model is for some reason in NLP always only conditioned on these features from a distributional semantic model, but not also on all the other features that you have some observed data for. And in missing data terms, this is called single regression mean imputation, conditioning on only auxiliary variables and not conditioning on any analysis model variables. if you ask a person who knows about multiple or imputation methods as ways of dealing with missing data, they're going to tell you this is a terrible way to impute missing data. It's just, from even the foundational texts on imputing missing data, it's almost certainly going to give you bias and overconfidence in any analysis you do on the filled in data. So what ELIP tries to do is do something similar, predict the missing data from distributional semantic models, but in a way that actually accords with the statistical theory on multiple imputation, it's called. So now I'll talk about this method. So how ELIP does it is with a thing called multiple imputation. The idea is you create M versions of the missing data where you sample those missing those values from a Bayesian model that's conditioned not only on a distributional semantic model, but all the observed data that we have. The concept here is that you want to take as much information in your observed data as possible into account, and drawing from a Bayesian posterior lets you get what we want, really, which is that estimator that has this nice property that it should converge over time to what the same estimates as we would get from complete data. So what you do, you draw, these M imputed values from a posterior distribution. Yeah, again, conditioned on all that open source data we have and features from NLP. And again, missing data people will tell you this is how you need to construct an imputation model if you want to impute in a sensible way. And as well, the really nice thing about drawing from the Bayesian posterior is it allows you the construction of confidence and credible intervals around your estimate of theta that actually will, under ideal conditions, be nominal. So you can take uncertainty that missing data introduces into account explicitly in your statistical inference. So what this means is that this resource I've developed is unique in that it allows you to say, maybe I do need observed data in this case. I can't actually safely reject this null because there's too much uncertainty in my model of the missing data. No other method, no other in NLP that I've seen that has of filling in this kind of missing lexical data has done this. None that I've found. Okay, so this is just a quick visualization of multiple imputation where you have your incomplete data, you produce multiple versions, plausible versions of the data where the observed data is the same, the light blue, and the missing data, the dark blue, varies. You repeat your analysis over these M plausible versions of your data, and then you pool those results together, do that adjustment for your inference. But this is actually a really challenging imputation task because the data is really high dimensional. So you have these 300 dimensional word vectors from a distributional semantic model, 450 plus lexical features, and a big mixture of missing of types of variables, continuous, bounded, continuous, count, and categorical. So as well, one challenge with imputation is that the assumptions that the imputer makes carries into the later analyses. So if I assume that there's like a linear relationship between two variables, and you, later analysts of the data, want to test a non-linearity, you can't, at least not in a way that will give you an unbiased estimate. So there's a strong push to use a flexible imputation method, but flexible imputation in really high dimensions is really hard. And so the first method that I tried actually couldn't handle my data, and that was a random forest. And the reason random forest didn't just crashed and burned is this issue where random forests can't extrapolate at all. They can interpolate beautifully within the range of your data, but as soon as you need to do some prediction outside the range of the data you have, they will crash and burn. And so these two bottom plots here are showing you that for two kinds of tree-based random forest and another tree-based method. But good old-fashioned linear regression can of course do this beautifully, because as long as it's linear. But a neural network can. A neural network under ideal conditions can do the same kind of extrapolation beyond the boundaries of the data. That's why I had to turn to deep learning in this case. The sort of off-the-shelf flexible methods couldn't handle it. And so I'm using a method called the multiple imputation importance weighted autoencoder, which is a species of variational autoencoder. So an autoencoder is a deep neural network that takes your input data and puts it through a series of nonlinear transformations and reduces the dimensions of your data down to what's called a latent space. And the part of the neural network that does that is called the encoder. From the latent space, you then extract the latent representations for the data and try to reconstruct the data. A variational autoencoder is a kind of autoencoder that, rather than producing a deterministic latent space where every input is encoded as a point, instead the latent space encodes probability distributions. And the data is reconstructed from samples from that probability distribution. And there's also a prior placed over the latent space that requires, that prevents overfitting. And what that does is turn this deep neural network into a generative model, a Bayesian generative model. Where the importance weighting comes in is that there's work done showing that if you have a variational autoencoder, if you take multiple samples, k samples from the latent space, and then calculate what's called an importance weight, you can turn a simple probability distribution, like a good old-fashioned, in this case, just a simple Gaussian, into a more complex posterior. And what's really nice about this kind of autoencoder is you can, by increasing the number of samples, get as k goes to infinity, close to what you would get with an analytical. If you could solve this, your Bayesian posterior, if you could get that posterior analytically, which is intractable in most cases. So what this multiple imputation importance weighted autoencoder does is use this importance sampling mechanism to deal with the presence of missing data in the input, where what the original creators show is that if you just literally fill in any missing portions of the input with just a 0, as long as k is the number of importance samples is sufficiently high, the presence of missing data doesn't matter. You can reconstruct a sort of complete picture of your data from partial input through an importance sampling mechanism. And so this is what the full model used to create ELIP looks like. Where this is the ELIP encoder, and on the other side is the decoder. So you have a mask, your data, and a learned placeholder value that just fills in the data. And then this is put through 2 fully connected layers. And then rather than a Gaussian, it encodes a student T distribution. And again, there's a Gaussian prior placed over the latent space. Then in the decoder, you take your k samples from that student T distribution and put them through the decoder. And then there are different kinds of output probability distributions depending on what kind of variable it is. If it's bounded, if it's positive only, whatever. And these connections, these lines here are concatenation skip connections, which have been shown to improve the quality of reconstructions in a variational autoencoder. Okay. I'm going to skip over this. This is the details of the calculation of the importance weights. If you're curious, we can go back to this slide later. But so here's ELIP and the model used to create it in a picture, right? So you have unstructured natural language data that's turned into a high dimensional black box representation for words through a distribution of semantic model, and that's one input. The other input is all of our experimental word processing recordings and our existing other kinds of lexical data that I just called word feature norms here. That goes into this autoencoder. The autoencoder yields M plausible complete data sets, that you analyze m times, and hopefully there learn whatever you want to learn about behavior, language, and cognition. And what I can say about the overall accuracy, so this is just different accuracy metrics depending on if it's a categorical, continuous, or count variable of the cross-validated accuracy of the model. And the point here is that the accuracy for most of the semantic variables is like really, really good. And then this is the reconstructions of the behavioral, mostly the second peak here in this distribution that looks a little bimodal is the reconstructions of the behavioral data, which is just more noisy. Experimental word processing data tends to be pretty noisy, which is why it's here. But you know, the model works brilliantly. It's at the state of the art of these sort of methods that have been used in NLP before that produce sort of deterministic predictions for missing at least semantic variables. Okay, so that's the key methodological innovation, this multiple imputation importance weighted autoencoder that allows you to recreate this data. So I'll finish off now with just a couple examples, little fun examples of use cases of the project. And these, I should say, this data is like hot off the press, and because it's a huge data set and there's so many questions you would ask, you know, these are just my first little attempts. They're not meant to be, you know, big intellectual contributions. They're just showing the kind of things you can do. So another question that a lot of people ask in cognitive science about words is why we learn some words before others. You know, children systematically acquire certain kinds of words earlier than others, and there are different theories about why that is. What you know, is it about communicative efficiency? Is it you know, is it this concreteness effect thing happening where kids learn the concrete words first? And what allows children to, you know, quickly learn language is this big, huge question in linguistics and cognitive science. And so this is a little example of asking a question about that, why we learn some words before others. And so what I'll ask is, does the colorfulness of a word predict the age at which you learn it after controlling for word concreteness and word frequency? So with how often you've been exposed to a word held constant, and whether that word denotes something you can see or touch held constant, does, you know, having a vivid color, you know, help you learn that word when you're a child or not? And this is what happens when you do what we would normally do with this kind of data, which is a complete case analysis, where there are only something like 400 and some words with colorfulness norms that are open source and published. And what this shows you is that there seems to be this linear decrease in the age at which you learn a word, depending on its colorfulness. So really colorful words, even controlling for that, you can, you know, see and touch the word, and you've heard it the same that this would suggest we actually do learn those earlier, which might be very interesting if you're a cognitive scientist. But what about what we're missing? What about all the rest of the lexicon, right? Well, here's what you see then, and this is done over 32 imputations, each line here and each confidence or interval. I haven't done any pooling. This is just what happens when you analyze the 32 draws from the ellip posterior. And this is done with 60,000 words, a sort of very representative sample of words that we know how many people know them. And so, you know, here there's like a tiny little increase in the colorfulness of a word, and then nothing, right? And this is flat over the higher ranges of colorfulness. So this is to again show you the possibility of these sampling biases changing what you would qualitatively conclude that if you just analyze these biased samples of words, you can make an opposite conclusion. When you take all the words that exist in English into account, you don't decide the same thing. Another reason why ELIP, I think, is very cool is that, again, unlike these distributional semantic model features, ELIP features are interpretable. They're based on the sum total of our theory about words, and they're the important features of words, cognitively speaking. Which means in the ELIP feature space, unlike in a DSM where you don't know what the coordinates mean, in ELIP you can actually encode a concept as a point in the feature space. And then you can measure something like a Euclidean distance in the feature space from that point as a way of understanding which words are related to that concept. And so this is an example of that where I've asked, as a way of exploring, say, gender stereotypes. We have some words that have been rated for their association with masculinity and femininity, and other words that have been rated for how much they relate to cognition, thinking. And I've restricted things here to words close to the middle range of word frequency. And so I'm going to show you two plots where the size in each plot is going to go of the word, and the plot is going to go from less gendered to more gendered. And the color, as sort of it goes darker, is going from light to dark, is going to show you the less cognitive to more cognitive words. And so here's the words associated with femininity, and it's compassion, insight, passionate, lots of sort of positive, thinky words. I'll leave this up for a second and take a sip of my drink so you can take a look. And here's the masculine words, right? Where there's more stuff about sort of like negative emotion and like sort of immorality and these kind of things, which I think is pretty interesting. But again, with a kind of traditional distributional semantic model, you wouldn't have any way of defining a concept other than to sort of build an exemplar out of an existing word. With the ELIP, you don't have to do that. You can explicitly define precisely the concept you want to recover and recover the words that are sort of semantically closest to that concept. And even with there are sort of species of distributional semantic models out there that are more interpretable. Like there's one called a topic model, but those models are still only data driven. Whereas this is really based on the idea that, the associations with gender for words and the associations with cognition are one theoretically important dimension of meaning, or two theoretically important dimensions of meaning. Okay, so to summarize everything, so this English Lexicon Imputation project is a new resource of quantitative data on English words. It uses a mixture of natural language processing, Bayesian deep learning, and missing data methodology to correct the non-random, non-overlapping holes in all open source resources on English words that I could find that are available in cognitive science. And it also tries to correct this widespread and I think really problematic use of complete case analysis, which, again, I'm pointing the finger at my field here, but I'm really I've done this, naively before I learned about missing data. And so my hope is that we can sort of forge a better path forward using, if not ELIP itself, the method, other resources created using it, or inspire other people to design a better tool for dealing with the same problem. Better than complete case analysis anyway. So again, the data is kind of hot off the presses. I'm hoping to have a public release of it soon. Email me if you want to keep you updated on the public release, and I can tell you when it comes out. And the plan as well, I've written all the core code in ELIP with later usable implementation in mind. So I'm planning on producing an R package that gives a sort of easy interface to this Niue autoencoder, because the only other implementations out there are research code, not like a general purpose software package. And again, the hope is that by sharing that, we'll have an ELIP for every language and every purpose, or people will be able to outdo me and create a better version of ELIP. Okay, that's it for me. Thank you very much for listening.
Thank you, Bryor. Any questions? Please raise your hand. Elisa.
Can you talk a little bit about how words were defined as feminine or masculine?
Oh yeah, sure. So there's existing like in the same way you can ask, on a scale of 1 to 7, how concrete is a word or how abstract is a word. Some people in the past have asked about, on a scale of 1 to 1 to whatever, what words are most associated with masculinity and femininity. I don't know what the actual instructions were used in that study off the top of my head, but that's how, with just a Likert scale and showing words one at a time and asking people.
Okay, thank you.
Any other question or comments? Susan.
Yeah, sorry, I don't have that strong a math background. I attended this talk because it sounded potentially applicable to something I'm trying to do, and I just wanted to get your opinion about whether this might be a helpful approach. I have a long-term study of capuchin monkeys, and I've been recording every behavior that they do, really insanely detailed protocols for the last 32 years with the aim of studying cultural dynamics. So I know that there's social transmission, there's a lot of innovation, and also I'm interested in how behavioral repertoire size and content changes over the course of the lifespan.
Right.
And it's an observational study, so I do have terrible sampling bias. You can't really find a wild monkey group when you want to find it necessarily, and can't get even sampling. So I've been looking for a way to determine what the probable actual repertoire size is, especially during periods of undersampling.
Right.
Do you think that this approach that you're describing would help solve my problems? And if so, could you direct me to the kinds of sources that you used to learn how to do this to begin with?
Yeah, sure. So, just the sort of foundational kind of books on missing data would be a good place to go to. So there's work by Rubin. He laid down the sort of early work, and then there's an R package called MICE, multiple imputation by chained equations, which has lots of extensive tutorials and information on how to do that. And there's also a great book by UCLA's own Craig Enders, a textbook on missing data methods. That's also very good.
Okay.
What I will say about the method in particular is multiple imputation gets really thorny when you have, say, like a time series, and when you have nested observations, like say multiple observations from the same monkey over time, which I imagine you have. So even ELIP, one of its big limitation is actually that it only imputes at the level of like individual words and not as well people and their particular, like, so it doesn't do trial level experimental data, for example. It doesn't impute like, the representation for my word in this particular context. And it's just that, taking account those nested data is brutally hard. And
that's what I was afraid of. Okay, thanks.
Any other question? Yes, Abhi.
Okay. Well, first, very interesting talk. Thank you, Bryor. I really enjoyed it. I have a very simple question. How is a word missing in one of the data sets you're using? Like, what does it mean when it's missing exactly?
Yes, so it means that someone had some sample of words that they either used in an experiment, or that they took some measurement for, like they normed it for concreteness. But we know that other words exist primarily because of corpora, right? So you can go into a corpus of natural language and see that somebody uses a word like thinking, but all the data sets that we have only have the word think in them, because like you're less likely to norm the verb, for example. This is another systematic reason the data is missing. So yeah,
Okay.
it just means we have, it's actually one of the reasons it's really nice to be a linguist. We have so much data on the words people use. We like know that that word exists, but like we don't have data for it.
Right. Okay. Thank you.
Any other question?
I think it's Susan has a hand raised.
That's
Oh, I think I just didn't take it down from.
Oh,
before.
okay.
Sorry, I'll take it down.
not. I have a simple question. So there are many words in English that have different meaning in different cultures. And depending on the background of a person, they might have different reactions to those words.
Yep.
So how do you take care of those kind of cases? I mean, that might be very corner case, but I think
no, it's exactly what I want to work on with extensions of the resource actually, and the method. Because it's so expensive to collect even like a population level average, there's a lot of neglect of individual variation in meaning. And so I think, you know, we make like very problematic and strong assumptions in our experiments even now, where we like assume that, you know, everyone's going to have the same emotional reactions to words. And I would be very surprised if people do. So the hope is to later adapt the method in a couple of ways. One thing you can actually change is you can change the black box NLP representations to word like a distributional semantic model trained on a particular corpus. So, you know, I could, you know, if I did sample of say a Twitter that was say just Canadians, I could produce a Canadian version, for example. The other way is, again, this extension, like I just talked about, that's really hard to allow you to predict an individual person's judgments, which is something I want to figure out, but it's just really hard because of dealing with the dealing with nested data in this paradigm is very tricky.
thank you. I mean, very common words like gift might have a entirely different meaning in different.
Yeah, and the hope is that if there's sort of ambiguity, that would be reflected in the posterior of the model, right? And so if there's sort of that, and so the hope is as well that kind of, we can incorporate that kind of uncertainty, or even just have, you know, there are some measurements in ELIP of ambiguity. And so, you know, it's possible to at least try to, you know, include an interaction between ambiguity and whatever feature, so we can verify that, you know, that ambiguity isn't moderating the experimental effect we observe.
Thank you. Any other question or comment? If not, let's thank Bryor. It's a really good presentation and very good topic. It's very interesting. So I think Bryor is planning on having a workshop in next few months. Hopefully you will receive the notification for that, and maybe join over there if you have further interest in these things. So thank you again.
Yeah, thanks everyone so much.
Excellent. Thank you.
Thank you.